We need to determine the deflection curve for the cantilever beam shown on the figure, which is subjected to two concentrated loads of equal magnitude, one of them applied at midspan and the other one applied at the tip of the cantilever. And we are told that the flexural rigidity of the beam is constant. We are going to be using the discontinuity functions method, so what we need to do first is draw the free body diagram with all the externally applied forces as well as the external reactions. So here we have the reactions at the fixed support. Remember that a fixed support prevents translation along the horizontal and vertical directions, so there are going to be reaction forces along those two directions. In this case, because we don't have any horizontal force, the support is not going to have a horizontal reaction force, but the vertical reaction force is going upwards and the magnitude is 2p. There is going to be a reaction moment, so we take summation of moments equals 0, and we find that the reaction moment at the support is a negative bending moment because it's causing compression at the bottom and tension at the top, and the value is 3pl over 2. So once that we have the free body diagram of the system with all the externally applied forces as well as the reaction forces, we are going to be writing the equation for the bending moment of the beam. And we are going to be using these two discontinuity functions or Macaulay functions that represent what is the bending moment due to a concentrated load, that is on the left side of the screen, and what is the bending moment caused by a couple, and that is shown on the right side of the screen. We are going to start at the fixed support, so the first thing that we are going to be looking is at the concentrated load 2p, so that's a Macaulay function that would follow this format. Because the load is going upwards, this sign is going to be positive, the magnitude of the load is 2p, and then we have the Macaulay function of x minus the coordinate where it's acting, which is 0. We move to the couple, which is the reaction moment at the fixed support, and that is going to follow this function. So we have both the reaction moment in our system and the couple applied here have the same direction, so we follow with this negative sign. It would be minus the magnitude of the couple, which is 3pl over 2, and then we have the Macaulay function of x minus the coordinate where that moment is acting, which is 0, and that Macaulay function is to the power of 0 as shown here. We move to the concentrated load at midspan, so we would have, again, we look at this function, minus p, the load is going downwards, the magnitude is p, and then we have the Macaulay function x minus the coordinate where it's acting, which is L over 2. And finally, we have the concentrated load at the tip is going downwards, so it would be minus p, Macaulay function of x minus the coordinate where it's acting, which is L. Note that we can simplify this expression. The last term in this equation is always going to be 0, because x is always going to be lower or equal than L, and in this case the Macaulay function will always go to 0. And we have here the simplified expression when we have a function here of x minus 0, because all the x are going to be greater or equal than 0, we can simplify that as 2px. And the same thing here, we have x minus 0 is always going to be x to the power of 0. So once that we have the bending moment equation, we proceed to the beam equation that relates the bending moment to the second derivative of the deflection. Because we have a constant flexural rigidity, we can pass that to the left hand side, and we end up with this expression. So basically we integrate the left hand side twice to obtain the deflection curve, and we integrate twice the moment. The first integral is going to give us the slope of the rotation at any point along the beam, and note that we have to add a constant of integration. And the second integral will give us the deflection at any point x, and we have to add also another constant of integration. So before we can finish the problem saying these are the equations that give us either the slope or the deflection at any point x, we need to specify the values of those constants of integration, and for that we are going to be looking at the boundary conditions of the problem. in this case, the support condition. So if we look at the support, we know two things about how the beam behaves at this point. Remember, this support is preventing translation along the horizontal, so that means that the beam has zero deflection at that point. So at x equals 0, v is equal 0. And likewise, we have a reaction moment, this reaction moment that is preventing rotation at that point. So at x equals 0, the rotation or slope is equal to 0 as well. So let's write those down. The first one is the deflection at x equals 0 is equal to 0. We substitute that into equation 2 and we find the constant of integration is 0. The second boundary condition is the slope or rotation is 0 at x equals 0. Substitute into equation 1 and we find that the first constant of integration is also equal to 0. Substitute into equations 1 and 2 and we find the equations for the slope and the deflection at any point along the beam.